Hello, my name is Blake Barnard. I am a Systems Specialist on Team 525, Textron Aviation Product Support. In this video today, we will be discussing the environmental control system on the models 525, 525A, and 525B Citation aircraft. Please note that this video is informational only and does not constitute instructions for continued airworthiness for maintaining the aircraft. Please refer to the applicable aircraft maintenance manual. I will also note that this discussion does not refer to anything related to the CJ4 or 525C model. If I reference all CJs or all 525s in the presentation, please know and understand that I am not referring to the CJ4. Our purpose today is to familiarize pilots and technicians with the environmental system design, its operation, and maintenance. We are going to identify the major subsystems and components and talk about the differences between the models as well as the similarities. We'll cover normal operation, and we'll also discuss some common temperature control issues and how to do some troubleshooting. To start, we're going to talk about three subsystems: the pneumatics, the pressurization, and the temperature control. Pneumatics consists of taking bleed air off of the engine and cooling it down to use in the systems. Pressurization will include how we bring the air in, our inflow control, and how we control how it goes out of the pressure vessel. And temperature control, heating as well as vapor cycle cooling. This is an overview out of the CJ2 Plus Operator's Manual. It's pretty indicative of how most of the systems are on the CJs. They vary a little bit, but this is a good overview. As I mentioned, we start with bleed air that is extracted off of the engine, which goes through a pre-cooler and then goes to the pressure regulating shutoff valve and the flow control valve. There's also a service air portion of the system, as well as ram air that is used for cooling. We use a heat exchanger to cool the air down coming into the cabin. And there is also a fresh air fan that is available to pull outside air into the cabin if needed. We also use bleed air for engine anti-ice capability, wing anti-ice, and windshield anti-ice. Additionally, we use that same plumbing for emergency pressurization air. This is an overview, and we'll go into each of these areas in more detail, except for the anti-ice systems. So to start, we extract high-pressure bleed air off of the engines. There's two ports. This is a side view of one of the Williams FJ44 engines that we use. And we use two ports on the bottom of the engine and send that bleed air aft towards the rest of the system. We do have a little pathway that goes up to the engine anti-ice. That air basically remains stagnant unless the engine anti-ice is active, and then it flows forward to the piccolo tube on the engine nacelle. We also use fan bypass air to cool the pre-cooler system. We'll talk about that in a minute. That is the rule. Now here's the exception. On the 525, serials 1 through 599, we don't use fan bypass air. We actually use more of a ram air system. If you're standing underneath a pylon on this aircraft, you're going to look up and see a vent of sorts at the bottom. That's actually the inlet to the pre-cooler system. There's an actuator that moves forward and aft an arm that controls an exhaust door, and as the exhaust door moves open or closed, more or less ram air is flowing through that pre-cooler to cool that engine bleed air down. Then it's exhausted overboard. Now, as I mentioned, that was kind of the exception. Here's the rule. On 525 serial 600 and on, including M2, and on all 525A and 525B serials, we use the fan bypass air. There is a modulating valve shown here that actuates using service air pressure, and it controls how much flow comes into the inlet of the pre-cooler. So instead of controlling the escape, we control the inlet. and that is coming straight off the engine. Now you'll note on the CJ3s, on serials 327 and on, there is a dedicated exhaust vent for this pre-cooler. The other aircraft, earlier aircraft on 525 and 525A, as well as the earlier serial numbers on the 525B, may not have this. They do not have this on these models. And the reason is that air is vented into the pylon itself. But we learned through experience that on the CJ3, that air was just a little bit too warm and it was starting to discolor some of the paint. And so we released a new design via Service Bulletin 525B 3602 that addresses this on the earlier serials, and we changed the design at 327 and on. So on the CJ3s, you may see this dedicated exhaust vent. On the M2s, the CJ2 Pluses, that is not there. It is not needed. So how do we control that? Well, we have a bimetallic pneumatic temperature probe that is in stream, downstream of the pre-cooler outlet. So if you're looking at the image on the left, the bottom right corner there, that is the outlet of the pre-cooler. The bleed air tubing goes inboard towards the center of the aircraft in the tail cone and then makes a 90-degree turn forward. At that 90-degree junction, we see this yellow bimetallic probe, and its purpose is to regulate the temperature. So it senses the temperature of the outlet, and then service air is coming in and reaches the head of that pneumatic temperature probe. You'll notice at the top right of that other small kind of inset picture, there's a T, and we're taking some of that service air going to this probe. And as that probe senses about 475 degrees Fahrenheit, that probe, the head cracks open and allows service air pressure to move on downstream to the modulating valve and open it. Then we use that modulating valve to rotate open and allow more cooling air through. There's also an overheat switch in the system just downstream of that probe. It's set to go off at about 550 degrees Fahrenheit. So the engine bleed air is coming off at about 800 to 900 degrees. And after it goes through the pre-cooler, we want it to read about 475 degrees. So we definitely want to know if it's hotter than that. So that overheat switch is set off to go at 550. Now there's another system that's tied in here on models 525 and 525B, as well as 525A serial 462 and on. We call it the Max Cool feature or Max Cool operation. And that, going back to that little T I mentioned just a minute ago, it goes to a solenoid valve, which is normally closed and is powered open when there are certain conditions that are existing. One is that the air conditioner is commanded on. So if the air conditioner is turned on, that means we're trying to cool everything down in the cabin as much as possible. We want to add extra cooling through the pre-cooler, and what happens is with that air conditioner command, that solenoid valve opens up and it allows 23 psi to bypass the pneumatic temperature probe and go straight to the modulating valve, which will then drive it to the full cold position or full cooling position, max cool. Now, there's a couple times when the air conditioner may be on that we don't want this to be active, and one of those is with the anti-ice on. So if that anti-ice switch is on, then it will not allow the max cool solenoid to open and allow flow through. The other is up at a certain altitude. We really don't need it up above, say, 18,000 feet. And I say that because on some of the models and serial numbers, we have a 30,000 foot barometric switch, and others we have an 18,000 foot barometric switch. But the point of it is to not allow that to operate above those altitudes because we simply don't need it. In fact, on those airplanes that have a 30,000 foot switch for this barometric switch in the system, if you were to ever replace those, there's actually the substitution is to replace it with the 18,000 foot switch. We find that we just don't need it above that temperature, or I'm sorry, that altitude. And there's that barometric switch in the circuit. All right, so once the air goes through the pre-cooler, it has a couple of pathways it can take. It can go to the anti-ice systems and the service air, which we're not really going to discuss today in this video. Instead, we're going to talk about where it comes into the cabin. That leads us to our next section, which is inflow control. So on the image there, in the circles on the left and right side, there are actually two valves that are literally clamped to each other. One is the pressure regulating shutoff valve, and its job is to regulate the pressure to about 16 psi differential. There is a sense line that feeds those valves and tells those valves how much pressure is actually in the cabin, and their purpose is to regulate to about 16 pressure differential so that you always have positive pressure coming into the cabin. The flow control valves regulate how much actual flow comes in, and on the screen there you'll see there's a 4 and an 8 listed. Those are the low flow and the high flow positions. In low flow, you would get 4 pounds per minute from each side. Those are cumulative and they add up to 8 pounds per minute of flow coming into the cabin. Now that would normally be when you're in both source. If you take your source select knob and go to left or to right, then we kick that valve up to high flow and it goes up to 8 flow on that side. So you really don't lose any flow coming into the cabin by going to single source. Now that's the rule. The exception is the CJ3. The low flow is actually set to 5 pounds per minute, so cumulative it is 10 pounds per minute in both. And when you go to single source, you're down to 8 pounds per minute. So slightly different, but not much. Again, those were kind of the rules. This is the exception. On the early 525 serials 1 through 339, we don't use the double PRSOV flow control valve combo. Instead, we have 2 bleed air shutoff valves, one for left, one on right, and its sole purpose is to shut off the flow. And then we have a single flow control shutoff valve which regulates flow and pressure after they've combined from the left and right sources. And again, it applies to just the early 525s. For 525, serial 340 and on, including M2 and all 525A and 525B, including CJ3+, we have this combo with 2 pressure regulating shutoff valves and 2 flow control valves. As I mentioned, there's a sense line that goes forward to the cabin. That little purple line on the image ties to each one and then goes to a single line which goes forward and just pokes right into the aft pressure bulkhead. There's a small piccolo tube on the forward side covered by your interior that you don't see, and that allows those valves to sense what pressure is in the cabin and regulate accordingly. The flow control valves are cross-tied electrically to the opposite PRSOV. And how that works is if you're in single source, everything's relaxed. There's no power going to any of the valves. The flow control valves are relaxed at the low flow state, and the PRSOVs are relaxed open. When you select single source, say you go to left-hand source, the left-hand flow control valve is going to be powered up to the high flow position, and the right opposite side, the right side PRSOV is going to be powered closed so that no flow goes through that valve. It essentially acts as a shutoff valve. In that way, we're able to keep those valves functioning in a teamwork environment that will allow them to provide basically the same amount of pressure and flow whether you're in single source or both. All right, moving downstream from those valves, we have a heat exchanger, which is after the valve or after the flow ties together, and it acts basically just like a radiator on your car. There are 2 flow paths. You have the hot air flow through one direction and cooling air flowing through the opposite direction. That goes forward to a check valve and then into the aft pressure bulkhead. Now on the screen you'll see on the right there is a kind of a large blue cylinder. That is your fresh air fan, and that's tied also to the plumbing, your cooling ram air plumbing. And it too is protected by a check valve just after the one that's circled. You'll see where those two tubes join, there is a kind of a little mini bulkhead. There's another check valve there, so that's protected from any backflow pressure. And then going into the cabin, there it hits a diverter valve, and the two ears up top go to the left and right side of the cabin. The larger bottom goes forward to the cockpit, and that runs all the way underneath your floorboards on the right side of the cabin up to just behind the co-pilot seat, and we'll show that later. How much airflow goes up to the cockpit is controlled by your cockpit air distribution knob or your slider on your GTC. In norm, you're sending about 60% of the air forward. We do that because there's going to be some heat loss in that air as it travels through. Even though the tubing is insulated, there's still enough heat loss. We want to send more than half of the air up to the cockpit. When you change that and go all the way up to max, that's a 4-position selector, but if you go all the way up to max, you're sending 90% of that air up to the cockpit. And that's good for flights where you don't have any passengers and if you want to stay warm, toasty in the cockpit. All right, so that's how the flow comes in. We control the pressurization by how much flow we actually let out. And on the older serial numbers, we have what's the CAPS 1. Basically, that's all of these CJs that we're talking about except for the M2 and the CJ3 Plus, so non-Garmin aircraft. We start up front with a mini controller, and this is on your tilt panel. You'll note that it looks like percentage signs. Those are sometimes mistaken for percentage signs. Those are actually double zeros. So if you look at the bottom window, it says 000. That means no rate up or down. If you see a 1 in there, that's actually a 100 foot per minute either climb or dive. If the number has a minus sign in front of it, that means the cabin is diving. If there's nothing in front of it, that means the cabin is climbing. We control that using the controller and sending a signal, a ground signal, to two solenoid valves, a climb and a dive solenoid, which is located on the primary outflow valve. Now those solenoids are always powered, and then the controller provides the ground input. It's a pulsing ground input to either the climb and dive solenoid. We have service air going to a vacuum ejector that can either provide some pressure or some vacuum based on the need, and then that in turn is controlled by either the climb or dive solenoid. That will allow the control chamber to either fill with pressure and close the valve, or be relieved of pressure and open the valve. So if you have any sort of issue where the valve doesn't seem to change, it's always trying to climb or always trying to dive, you may have a short to ground somewhere either on the valve or in the wiring between it and the controller. Now if you do have any kind of electrical malfunction on that system, the backup is the manual pressurization control valve. We call it the cherry picker. It's got a little red knob on a stick. And you can see from the image there are two vent paths. One is to the inside of the cabin, which is that blue pathway with a blue arrow. You use that to dive the cabin. You're using cabin pressure. When you vent that to the control chamber and the outflow valves, it will close the valves. The other pathway is on the bottom, and it's a purple line that goes forward. It says forward pressure bulkhead. It actually goes out that into the nose wheel well. There's another little piccolo tube, and that's where it gets its static air pressure, which is when you're flying, it's going to be lower than your cabin air pressure. So when you vent that way, it will climb the cabin. It will relieve the pressure in the control chamber. The cherry picker controls the secondary outflow valve, and they are tied pneumatically so that when one is commanding, the other is following. Okay, on the M2 and the CJ3 Plus, we have a different system called the CAPS 2 system. It operates on similar principles, but there's a lot less going on in the cockpit. It's more automatic. There is a controller that is located on the aft pressure bulkhead just above the two outflow valves, and we no longer call them primary and secondary. They're both outflow valves that are tied pneumatically to the controller. The controller has an internal pump for climb and another one for dive, and based on the flight plan that's entered into the system and the aircraft altitude, it will change the air pressure as needed to maintain pressurization. We do have indications up on the multifunction display up in the cockpit, so you still have access to your cabin altitude, your cabin rate, and your delta pressure. But otherwise, it's pretty streamlined. There's a lot less flight crew involvement. There is a standby button that is used up front, so if one of those pumps gets stuck on and is always climbing or always diving, the standby button will arrest that, and essentially it's telling the controller to stop commanding. All right, so the air is coming in. We know how it's coming in and how pressure is maintained. How do we cool it down or warm it up? Well, for the heat control, as I mentioned, we have to cool that down. It's coming out of the pre-coolers at 475 degrees. We certainly don't want it that hot in the cabin. So we have ram air ducts. Those are on the forward ends of the pylon, the leading edges. You'll see a little hole on either side, and that plumbing ties together and runs up to a couple of places. For the cabin, we're looking at the cabin heat exchanger, and the amount of cooling flow going through there is determined by a butterfly valve in what we call the ram air modulating valve, and its purpose is to control how much cooling is going on based on the requirements of the system. That looks like this in the tail cone. So we have hot air coming from both left and right sides, ties together, goes through the heat exchanger. We have cooling air coming from the ram air scoops and filling up that plumbing. And then as it goes through the heat exchanger, we have cooled down bleed air that goes forward to the cabin. And we have warmed up ram air that is vented overboard. You'll see on the left there's kind of a brown-orange heat exchanger. The one on the left is the larger one, is the cabin heat exchanger. The one to the right, which is yellow, is your windshield bleed air heat exchanger. Similar operation for that one. Up front, we've got some controls that the flight crew can maintain for comfort up front. We're looking at the controller and the sensors here. So we have two modes. We have an auto control mode and a manual control mode. In auto, if you have a non-Garmin airplane, you're going to have a little rheostat on the tilt panel. It goes from all the way cold to all the way hot, and that's all auto temp. It's going to maintain temperature based on your selection. Also, there is a detent for the manual control, so if you go all the way to the cold side and then click it down into manual, then you can control it manually. On the Garmin airplanes, we have a slider. Does the same thing, sends a signal to the temperature controller that tells it what we are selecting up front. If you want manual, there's a switch on the panel. So you switch from norm to manual, and then you can use the manual toggle switch, which is on both airplanes. You can hold it in hot or cold, and it's spring-loaded to the center position. So just a tip, what we find sometimes is that if you're in the manual position, you want to use it to warm up the airplane. Say it's a little bit cooler than you like. You don't seem to be getting the heat that you want out of it. So you try to do it in manual. When you flip it to manual and hold it in the hot position, you're sending a direct signal to that ram air modulating valve to drive it full open. And that valve only takes about between 10 and 15 seconds to go from all the way cold to all the way hot. And so you're going to see an immediate effect in the plumbing just downstream of that, but you're not going to feel that up front for a while. I like to use the example of a kind of a radiator heat in the old buildings. Because we're controlling the amount of flow going out of the aircraft, it takes about 2 minutes for a full air load, all the air that's in the cabin, to be fully exchanged. A complete exchange takes about 2 minutes in these airplanes. So it's going to take some time for you to actually feel any temperature increase. So what often happens is we kind of expect it to act more like our car. We're going to turn it hot immediately. We feel an immediate change on our feet and everything's great. Well, that doesn't happen on this airplane. Instead, our technique that we recommend is to hold it in the hot or cold position, whichever way you're going, for 1 second, and then let it sit for 5 minutes. Don't touch anything. Let it stabilize. Let that air exchange happen. Let things take effect from what you've done in the tail cone to what you're actually feeling in the cabin and cockpit. If we do that, then we can creep up on, say we're trying to warm it up, we can creep up on that selected temperature without getting a duct overheat. And that's often what will happen if you hold that in the hot position. You'll get a duct overheat way before you'll feel any change up front. So we recommend doing that. There's actually a separate video, it's about 5 minutes long, that talks about how to use manual control on the CJ series, and that's exactly what I'm talking about there. So we've got some sensors in the cabin that will help us understand what's going on, help the controller determine based on what you've selected up front and what's going on in the cabin, whether it needs to warm up or cool down. The cabin temp sensor is located on a bracket just inside the vent, the inlet for the aft evaporator. The aft evaporator is located at the very back of the cabin. You're going to see it in the drop aisle. There's a little slit, it's about 1 inch tall, right above the carpet, and there should be a placard right in front of it that says do not block air vent, something to that effect. We want to make sure that's free and clear. So if you start to have temp control problems, one of the first things I always ask, is there anything in front of the aft evaporator? Because if we stop flow to that, if we stop flow over that sensor, you're going to have erroneous cabin temp readings, and then that's going to mess with what your controller is actually believing is going on. Now, one other thing I'd like to point out, in the AFM, there is a note that you do need to have your air conditioning switch in either auto or fan only. And again, it's because the aft evaporator fan is what's drawing air over that cabin temp sensor. And if that fan stops working, if you switch air conditioning to off thinking you don't need the air conditioner, it's going to kill that fan, which is going to stop flowing air over that cabin temp sensor and can cause some issues there. Just right next to that is a little thermistor. It's basically just there to sense the air temperature and convert it into a resistance value. We set it to trigger around 65 degrees. On the ground, we don't have any forward momentum. We don't have any ram air that's going to come in and cool things down. So we don't want the hot bleed air coming in all the time, or we're just going to overwhelm the system and it's just going to get too hot while you're taxiing around or we're waiting for clearance. So we have the 65 degree thermistor, which talks to the environmental PC board, which then talks to the pressurization PC board, which will shut those PRSOVs off at 65 degrees in the cabin. That can cause some pressure bumps that you may notice. It's just a small 200 to 500 foot per minute bump, and we'll talk more about that in a little bit when we get into the troubleshooting section. All right, going back to the tail cone, we have the duct temp sensor. So in order for the controller to understand what the situation is, it needs to look at the cabin or the cockpit input of where you've selected the temperature. It needs to look at what's actually in the cabin using the cabin temp sensor, and we need to look at what the output of that heat exchanger is. So the duct temp sensor is just downstream of that heat exchanger, as well as the air duct overheat switch. And we want to alert the crew if that air duct is getting hotter than about 310 degrees, because that can cause some concern with the ducting. So there's a switch set to do that. So again, if you drive it really hot and you get that air duct overheat, the AFM is going to tell you to cool it back down, either in manual or auto. So we don't want to constantly overshoot what we're shooting for. As I mentioned, we just want to use that little blip method to creep up on the heat that we need using the manual method if we're in the manual control. And then in the tail cone also we have the controller. Now it's not green, it's actually a black box. There are two of them on the aft pressure bulkhead. One is for the cabin temp and one is for the windshield temp. They're actually different part numbers and are keyed differently, so you cannot connect the cannon plugs to either one. Thankfully we don't run the risk of mixing those up. But if you are looking for that box, be aware there's another one that looks similar to it back there as well. All right, let's talk about vapor cycle cooling. I'm not going to go into the theory and operation. I'm just going to tell you where the pieces are and kind of how they interact with the system. We start with a compressor and a condenser in the tail cone. Now on the M2 and all the straight 525s, this is a This is a module that is together. The compressor and the condenser are a single unit. We call it the pallet, and those are located in the tail cone. On the 525A and the 525B, they're separated from each other. And you'll notice on the A and the B, on this diagram it shows some grills on the right-hand side of the tail cone. If you go look at the aircraft, there's one above the pylon and then there's one below the pylon. The one below the pylon is your outlet to your condenser fan. And sometimes if you have problems with the air conditioner cycling on and off, especially if it's frequent, as in less than a minute and then it'll kick back on, go back and check the outflow of that condenser module outlet. Often, if the condenser fan is not working, you won't feel any flow coming out of there, and that will cause the system to cycle on and off due to the pressures not being where they should because the condenser is not working correctly. So that's something you can look for if you have air conditioner cycling issues. Moving into the cabin, we have an aft evaporator unit, and you can see that it is tied to the cabin or the overhead WEMAX. And a forward unit on the 525A and 525B, that's going to be on the left side of the cabin at the bottom of the cabinet. On the 525 and the M2, it's going to be on the right side, just aft of your side-facing seat. And of course, the cabin WEMAX, we find sometimes when we're troubleshooting temperature control systems that these get closed. Either a passenger or sometimes by maintenance, if they're in there working, they will close these, and then later on we get a cabin temp squawk, and come to find that it's just that the cabin WEMAX have been closed. So if you do see a change in your cabin temperature that's undesired, just make sure those are open so that the air conditioner can work correctly. Up front there is a grill that is fed by the forward evaporator between the pilot and co-pilot seat on the floor, and that is normally blowing cool air unless you select defog. Then at that point there's a little diverter valve that will shut off the air to the floor grill and send it forward to the defog fan. There's also a flood cooling option. If you look on your switches up on the pedestal or on your GTC, the aft fan has a flood position. And what that is doing is, you can see in the diagram on the right, the bottom red is the aft evaporator, and that big green plenum is kind of designed to trap moisture, condensation, and keep it out of the evaporator and fan assembly. And then it goes up through this grill and then up overhead into the cabin WEMAX. There are some pneumatically actuated, electrically controlled actuators that will open or close a little floodgate there in that yellow box assembly. And if you climb into the cabin and look all the way aft, you'll see a grill there. That's where that flood cooling is going to come out. It seems to help cool things down quicker if you use that aft flood position. Be aware though, for ground operations, if you don't have an engine running, they do require service air. So if you don't have an engine running, you're just using a GPU to run the air conditioner, you may not be able to control that aft flood cooling section there. And here is the switch there. Flood is in the up position on this switch. All right, so now we're looking at how the cockpit is heated and cooled, and you'll notice there's different plumbing for heating than there is for cooling, and that's by design. We do sometimes get new flight crew who are not used to this airplane. They'll say, well, my feet are always warm, but I'm always getting cold air blowing on me from overhead or from the forward vents, and that is because they are plumbed separately. They do not intermix. We've got warm air coming up from the diverter valve in the aft bulkhead area. As I mentioned, it comes all the way up the right side of the cockpit or the cabin, and then comes up to the right side of the cockpit. And you'll see there's a little tee off to go to blow a little bit of warm air on your side windows. That keeps them defrosted or defogged. And you'll notice too, there's a blue tube that goes through the center of this red warm air tube. That's because for defog, we don't want really cold air blowing on the windscreen. We want some air that's dry, but we want it to be warmed up. So it acts as somewhat of a heat exchanger. That cold air coming from the forward evaporator gets warmed up a little bit through the heat exchange function, or basically a tube inside a tube allows some heat transfer, and so that's why that's designed that way. As I mentioned, the cold air is coming from your forward evaporator and goes either to the defog side or up around the top to your overhead WEMAX and forward to your vents. That's where those tie together. We also have emergency pressurization air. As I mentioned, we use the windshield bleed air plumbing. So your windshield bleed air actually is turned on when you have selected emergency pressurization, and it dumps into that plenum, so it has that same feeder system. It will blow on your feet, and it will blow on the windscreen as well. All right, we're going to get into some troubleshooting now here. As you can see, there's quite a bit of components involved in this system, but we usually boil it down to either it's too hot or it's too cold, or in auto the temperature just kind of moves around on its own. It doesn't seem to find a good spot, seems erratic. And then also we get reports of pressure bumps while operating on the ground, especially on CJ3s. Well, before we dive into the troubleshooting, I'd like to let you know of a resource on our txtavsupport.com website. We have a checklist that's available to get flight data. Sometimes we need flight data to understand what's going on in the system. We can test the sensors, we can test the controller. There's things that we can do on the ground that's in the maintenance manual that allows us to do that. But we cannot duplicate that ram air that forward momentum is needed to bring into the system. And so if we're having trouble, if we've gone through all the tests on the ground, we can't find anything wrong, we may need some flight data. And so I would actually encourage you to go to our website. This is what it looks like here. You can select one of your models on the left. I've selected 525B, and then once that model page comes up, you'll find over on the right-hand side, the right-hand column, there's an additional information block, and you can see there's a flight control check. This is a checklist I'll show you here in a minute. On the 525B, we actually have the Garmin airplanes separate from the other airplanes, the Collins airplanes. The reason we do that is because the interface with the pilot is a little bit different. Instead of a GTC interface, we've got switches and knobs, and so we've made two checklists. They essentially gather the same information, but because the interfaces are different, they're a little bit different from one to another. Here is a view of the non-Garmin G3000 checklist, and it tells you how to set it up, and then this information that we're looking for is taken during cruise. And that doesn't really necessarily equate to a certain altitude. It's just when the airplane is stabilized, you're probably up around 30,000 feet or higher, and that allows us to do some testing. So as I mentioned, I would encourage you to go to our website and download this information and just have a copy of this checklist up front with you in case you start to get a temperature control issue. You can get that flight data right then, and that really helps the technician to troubleshoot what's going on. Often we get the squawk temp control in-op. We have no details. We have really nothing to go on. So really the only thing the technician can do is go through all the checks in the book. But again, as I mentioned, we may need flight data. So having that beforehand can save downtime and perhaps some troubleshooting time and effort and money. So the first squawk is too much heat. One of the things that we really look for when there's too much heat is ITT information. That may help us resolve or figure out what's going on. Not always, but that information is pretty critical, and that's again why I would suggest you have a copy of that checklist with you so that if things look like we need to start investigating a temp control issue, we can capture this data while the issue is occurring. All right, here's an example of the block on the checklist. Now, this particular example, I was working with a customer, and I know on the right side it says any noticeable change in temperature. It says cooler or okay or the same. It doesn't say hotter. In this case, we had been troubleshooting before, and he had He had had a too much heat squawk, and so I was looking for indications on the ITTs as to what might be causing that too much heat. Generally speaking, on the CJ aircraft, once you get up to altitude, because of the amount of air exchange going into the cabin, those outflow valves are going to be mostly closed. So there's actually not a lot of air flow through the cabin. And so generally what can happen on longer flights is the cabin can start to cold soak and it starts to get cooler. That's typically the squawk that we see because of the way the system operates and the design of the aircraft. However, if I get in too much heat up at cruise altitude, generally that means I've got too much bleed air coming in from somewhere. And so that's why I want to look at the ITT data. First, we want to match the engine's N1 speed as close as possible so that we can get accurate ITT reflection. So we're going to start in both. In this case, I noticed right off the bat the left engine ITT is about 10 degrees higher than the right. That may or may not be an issue, but it is worthy of note. Generally, I like to see them closer than that. Usually the splits I see when we're doing this troubleshooting is 10 to 20 degrees. This is 10, so it's noteworthy. Next, we're going to go to left-hand source. And remember in our discussion previously, when I go to left-hand source, my flow goes up from 4 to 8. So that's actually flowing more off of the engine, which is going to equate a higher ITT. So I would expect the left-hand ITT to increase. In this case, it's not. It's staying the same. So that's something else that could be key here. Now if I look at the right-hand engine, I'm shutting the right-hand PRSOV, so I'm actually drawing less bleed air off of the engine, which would allow it to run cooler, so the ITT should drop. In this case, it goes from 730 down to 710, so that's working right. Then I'm going to switch over to right-hand source. Well, in this case, I'm shutting off the left PRSOV, which would cause the ITT to drop, and it does. I'm going to high flow on the right side, so it should be higher than when we saw it in both. And so comparing both to right-hand source, it is up. It's about 10 degrees, so that looks good. And then when I go back to both, again, I should see on the left side, I should see the ITT go up because it was shut off for right-hand source, and now it should be coming back online. It does. And the right-hand ITT should drop down because it's going to low flow, and it does. So the real thing I'm looking at here is why didn't it go up when I selected left-hand source from when it was already in both? We determined that that flow control valve on the left side was actually stuck in the high position. Because it was stuck in high, it was adding 8 pounds per minute from the left side to 4 pounds per minute on the right side for a total of 12 pounds per minute of flow. That's too much bleed air coming into the system. The pressurization side can handle it, it can compensate, but all that hot bleed air couldn't be compensated by the temp control system, and that's why he was complaining about a hot cabin. All right, well, let's say you do that check and all the ITTs match and everything's good, but use the other side of that graph and say, you know what, in right-hand source, everything's nice. In left-hand source, it's hot. Well, then we start looking at the pre-cooler control. Maybe the pre-cooler on the left-hand side is running hotter. It can run up to 550 degrees before you'll get a bleed air overheat. Ideally, we're looking at 475, so that's a 75-degree difference, and that can actually cause things to be warmer in the cabin without triggering a bleed air overheat. So for a possible pre-cooler issue, we could look at maybe that pneumatic temperature probe is out of calibration, maybe it's opening late, and so it's causing things to run hotter. You could also have a service air leak that is either between the temperature probe and the modulating valve, or anywhere up to the temperature control valve. If we have a leak and we're not providing that service air when it's supposed to be provided, that would too cause it to run hot. All right, switching gears to the squawk where everything's cold. First thing I want to know is, does the air conditioner come on? Is it on all the time? Is it running? You know, if it's running all the time and it's way too cold in there, then we would look at maybe the ram air modulating valve. Is there something wrong on the valve itself to where it's not responding to the correct inputs? that valve will trigger the air conditioner to come on when it's fully open. And it will stay running until it reaches the halfway closed position. So if it's on all the time, for some reason that valve is open. It could be the valve itself, or it could be a sensor or something else. Another thing that we want to do is it just cold in the cockpit? Everything's fine in the cabin. We can isolate it using the air distribution knob or the slider. And in that way we can determine maybe we've got a duct issue or a leak. If the cabin and cockpit are not the same temperature, then that can help us isolate things. We may look at the diverter valve. I've seen the diverter valve actually had malfunction and shifted on the shaft and actually was closing off air to the cockpit. So the cabin was nice and toasty, but there was really no airflow into the cockpit because that valve had basically blocked airflow. All right, again, too cold. Let's see if the ITTs are matching. Maybe we've got something else going on. We can look at the pre-cooler control again. That would be, so that modulating valve there in green, service air line going to that has a little orifice in it, and that's to allow it to bleed down when the pneumatic temperature probe shuts off the bleed air. In other words, when that probe says, hey, it's time to warm up, I'm going to stop feeding the actuator to open the pre-cooler, it will shut off the service air, but that service air would be trapped if we didn't have an orifice. And if it was trapped, that modulating valve would remain fully open and allow cooling continually. So we put an orifice in there to allow it to bleed off, so the pressure can bleed off because that valve is spring-loaded to the closed position. So if that orifice gets plugged and that air isn't venting, it could run on the cold side. I've also seen the max cool solenoid fail open, so it's totally bypassing the normal control, that bimetallic probe. It's totally bypassing that and going straight to full cold. That would cause things to run cooler. Or again, if that pneumatic temperature probe is opening too early rather than too late, if it's opening too early, it's going to run things cooler. Also, for cold cabin or cockpit, I want to check, make sure we've got airflow. Now, you're not going to feel a lot of airflow coming into the cabin or the cockpit, but if you kind of wet your fingers and stick them by the vent, you should feel some breeze there. It's not going to be a lot, but if you can't feel anything, there's a possibility that we have a duct that's either blocked or has become disconnected and it's going out somewhere else. We find this often after the airplane has been through a major maintenance phase or a dock inspection. Things have been torn apart and then put back together. Sometimes they don't go back together correctly, or sometimes they get blocked. So we want to verify there's airflow. Especially concerning the cockpit. I have seen sometimes where that duct going forward gets crushed and kind of blocks off the air going forward. Also, believe it or not, a cabin leak. The pressurization system may be able to keep up with a cabin leak, but a cabin leak would actually cool the cabin down. So it's not out of the troubleshooting bag of tricks to pressurize the cabin and see what the leak rate is when we're looking at a cold issue. All right, next is our temperature fluctuates in auto. We get this fairly often. There's a couple things that we can look at to figure out what's going on. So generally speaking, one of the first questions that we ask is, have you tried operating a manual and can you maintain cabin temperature in manual? If you can, then that helps us focus on the auto side, either the control, the rheostat, or the controller, or any of the sensors. So on this one, we would look at, first and foremost, I always like to check the rheostat. It's probably the easiest thing to check, or one of the easiest things. It's also a fairly common failure point, and it's one of the least expensive to replace. So I always check the rheostat, and what you can do there is have a buddy in the back with a meter looking at the resistance changes on pins A and C there as you are up front going from the full cold to the full hot position. That rheostat is basically just a wiper going across the coil, and sometimes those wear out. That thing can be moved every flight, and sometimes they just wear out. And so what we're looking for is there's a limitation on what the cold resistance should be and what the warm resistance should be, and then we want to see a linear change, a nice smooth linear change. If there's a erratic jump at anywhere along that line, I would replace that rheostat, because what can happen is it can get a little sweet spot. Say you run it at 1 o'clock all the time, well, maybe that sweet spot develops around 1 o'clock, and it will vary the resistance. I've seen reports of not touching that resistor or that rheostat at all, and you're back in there with the meter and your resistance is climbing up and then going back down and it's moving all over. That would explain why your temperature is doing the same thing, because it thinks that you are moving it up or down when you're actually not touching it. Another thing I would look at too is if the inputs are good, we also want to make sure that the ram air modulating valve response is accurate per the inputs from the controller and the cockpit. Now, the rheostat check doesn't really work on the Garmin airplanes because it's a different input. It's a different controller on the Garmin airplanes, so we don't check the resistance that way. But for those older aircraft, that rheostat check is a good one. And the last squawk that we have often is the pressure bumps on the ground. We get this especially with CJ3 operators who are new to the aircraft. They're taxiing around. It seems to occur in either the springtime or the fall when the cabin temperature is roughly the same as the outside air temperature, and it's around 65 degrees. And as I mentioned, we shut off those PRSOVs when the cabin temperature gets above 65 degrees. Well, if the cabin temperature is hovering at that point, then what can happen is they shut off the PRSOVs, the cabin temperature drops a little bit because we no longer have incoming warm bleed air, hits that 65 degree set point, opens those PRSOVs, warms it up a little bit, takes it above 65, and it can cycle on and off like that. If you're not aware or familiar with it, it can be kind of concerning. It's not a big pressure bump. It's 200 to 500 foot per minute. You'll see it blip, and then it'll stabilize for a minute or so, and then you'll see it blip again. Sometimes the passengers complain, hey, we're getting this weird air noise. It seems to be cycling. What's happening is that thermistor is sending a signal to the environmental PC card, which then tells the pressurization PC card to shut those valves off. Now, this is actually how it's supposed to work. It's supposed to close those PRSOVs, and we've got a web article on our support website that explains this condition and basically how to mitigate it. So this kind of gives you some information on what to look for. Again, we just want to make sure it's cycling around that 65 degrees. The way to mitigate it is pretty easy. Go to manual temp control and don't touch it. Let it sit for a few minutes. What you're doing is you're bypassing that 65 degree circuit. When it's in manual, it turns on the PRSOVs, and you're going to dump some warm air in there. Let it sit for a few minutes, let it warm the cabin up to 70 degrees or so, and then go back to auto. And then at that point, it's not hovering around 65. It's not going to cycle on and off like it was, and you can go on your way. That's also helpful in troubleshooting. So if you do have on-the-ground bumps and you go to manual and they don't go away, then there is something that we do need to do a maintenance visit for and look at. All right, well, thank you for joining me today. I appreciate your time. We hope this has been helpful in discussing the environmental control system for the 525, 525A, and 525B aircraft models. If you have any questions concerning these airplanes, please contact Team 525 with the contact information on the screen. You can reach out to us via phone or email, and we appreciate your time today.